Hi, I'm Todd Austin, and this is the sixth and final episode of my six-part video tutorial on hardware security. In this final episode, we'll be examining emerging security protections. This is emerging research and industry technologies that work to address, in many cases, a broader set of threats as well as traditional threats in a more durable manner. This is the final episode of my six-part video tutorial sequence. In the first part, we set the stage on why hardware security is important. In the second part, we looked at the basics of security, cryptography, hashing signatures. In the third part, we looked at software hacking of software and hardware vulnerabilities. In the fourth part, we examined SideChannel attacks. In the fifth part, we looked at existing security defenses from a hardware and software perspective, those that are already out in the field. And in this final sixth part, we're going to look at some emerging defenses. So let's get started. First thing I want to take a look at are PUFs, physically unclonable functions. They solve a really unique and interesting problem in the world of security, which is how do we authenticate devices? How do we know that we're interacting with a specific device, be it a key card or a credit card, or whether electronics are genuine or whether they've been produced in a way that, overproduced? We can look at these signatures that PUF creates, and it's essentially a unique identifier for every piece of silicon that is manufactured. The way PUFs work is they translate the process variation in the underlying silicon electronics into a probable function that's very difficult to learn and recreate in software. And so what is process variation? Process variation occurs when you have a silicon chip that's been manufactured. In today's silicon, the dimensions of transistors are very small. We have transistors that are literally tens of atoms in width. And so small variations in the width of an atom, width of a transistor, if it's 15 versus 16 versus 14 atoms in width, that creates some speed and power variation in those devices. And designers, when they design circuits, they basically have tools and methodologies to try and hide all these variations from the overall system. But if we build a circuit that leans into those variations, we can use those variations to identify a specific chip. So this is a arbiter-based PUF. And what you can see here is we're going to give a challenge. It's an n-bit challenge, typically large, 64 or 128 bits. And what the challenge bits are going to do is they're going to determine if these muxes here pass straight through or if they swap the value as they go through. They're going to determine if the top value goes through or the bottom value goes through. And then with that, they'll determine as a pair whether the value goes through straight or swaps. And so we can see as an example, if I give 1, 0, 1, we'll get a swap on the first set. We'll get no swap on the second set, and then no swap on the third set. And so what that'll do is that'll create a single path through there for the blue line and another path for the gray line. Now, depending on how they swap, the one on the top that comes out on the top is going to be the input to a latch, the Q, the D value, and the bottom one is going to be the clock to the latch. And so now, of course, if I have n bits of challenge, I then have 2 to n different paths that I can take through this device, and each of those paths will have its own unique process variation. And so which one of those bits arrives first at the output will be determined by that unique process variation. if the D arrives before the G, then I get a 1 output. If the D arrives after the G, then I get a 0 input. So it's a really cool approach to measure process variation. And so what I do is if I want to identify a chip, I give it my challenges, my n-bit challenges, and then I record for that particular chip, what are the outputs? 0, 0, 1, 1, 0, 0, 1 for these challenge. And then if I come back and do those challenges again, I can see, am I still on the same chip that I was previously? I'm basically, measuring. And then the reason why it's essentially unclonable is because, with an n-bit challenge, I'd have to do 2 to the n probes. So if it's 128 length challenge sequence, then I'd have to do 2 to the 128 different probes. And I can't do that many probes. But interestingly enough, there's some pretty interesting attacks on these puffs in terms of machine learning, where machine learning can kind of figure out, there's only 128 stages there. So machine learning can basically figure out what the process variation on each of those 128 stages is, and then can start answering questions to challenges that's never seen before. So these, it sounds like there's a huge amount of entropy here, but, there may not always be a lot of entropy. And so there's a lot of research on how to sort of really ramp up that entropy. There's also some concerns with aging as well. As transistors age, they can get slower. And does that change the results of these probes? So there's various concerns here, but what's really interesting about this technology is it can give you essentially a secret on a chip that nobody knows. So let's say, for example, you have a trusted platform module on a chip, and you want that module to have its own private and public asymmetric key pair. You could use a puff, for example, to create the secret key, then run an algorithm, generate the public key, export that to some certifying authority. And now you have a secret key in your TPM that nobody knows. Only the TPM hardware has access to that. So these are really exciting technologies to put into silicon. Okay. Another really interesting silicon technology is logic locking. The goal with the logic locking is to basically prevent an IC from having unauthorized bring up or enablement and theft. So when you manufacture chips, if your chips are not logic locked, then the fab could potentially make extra chips without your knowledge and then sell them on the black market. So what logic locking does is it basically locks down the chip. So if you don't have the key to the chip, then you can't turn it on. And this technology actually works great with the previous slides technology, puffs. So we could know what is, we can associate each of those puff values with being a chip that I intended to manufacture. If I see that's a chip that I intended to manufacture, then I will export into that using secret keys based on that puff, the unlock key for this chip. Once you unlock the logic locking, then the chip can operate as it was intended. The other thing that logic locking helps with is what's called reverse engineering. There's companies out there which literally take a new chip and they just start, lasering away layers of the silicon and studying how the circuits are built because they want to reverse engineer the chip. And this can help with that as well. And the reason why this helps with stopping overproduction and reverse engineering is because you essentially haven't finished the design until you've loaded the key into the logic locks. So the basic approach is we're going to do what they call encryption. It's not really encryption. It's just we're going to just drop some XORs into onto wires where there would potentially be an inverter, and then on other wires where there was not an inverter. And then essentially what the key tells us is where there are inverters and where there are not inverters. If a 0 goes in to the key bit, that's just a pass through of that line. And if a 1 goes into that, then it acts as an inverter, that XOR gate. So essentially with the key bits, you're telling where do all these missing inverters go in my design. And if I install those missing inverters wrong, guess the wrong key, then the design doesn't work. If I install the inverters correctly, correct key, then the design all of a sudden starts to work. So it's a really cool technology. Again, it seems like with n key bits, there's 2 to the n different combinations, but people can look at circuits and go, oh yeah, that's an adder, that's an inverter, that's not an inverter. There's lots of ways to reverse engineer these, and people have also again demonstrated satisfiability tools as well as machine learning tools can really punch into this these technologies and figure out what those key values should be by basically trying to understand the circuits. But overall, really interesting technology that really allows a vendor to prevent anyone from turning on their chips until they can tell that they were, legally manufactured. In the previous lecture, we talked about how with tools like PointGuard, encrypting pointers makes it difficult to forge pointers. And when you can't forge pointers, you can't bring pointers from the outside world into your security attack. And that throws a wrench into a lot of different security attacks. ARM, which is a processor manufacturing company out of the UK, has a technology called ARM PAC, which is a pointer authentication code technology. And they don't encrypt the pointers. Instead, what they do is they produce a hash of the pointer value. Then they encrypt that hash. That creates what's called the PAC, and that gets tucked into the upper part of the address. This is for a 64-bit machine where it doesn't actually have a 64-bit address space. Typically, the upper 16 bits of a 64-bit machine are unused because nobody needs more than a 48-bit address space. Well, maybe not, but that's a very large address space. So on a lot of machines, the upper 16 bits of the virtual address space are not used. So what PAC does is it just tucks an encrypted hash up into that upper bits. And so with an encrypted hash, we can, whenever we generate a new pointer in pointer arithmetic, or when we take the address of something, the hardware has this internal key. It generates the hash, it encrypts the hash, and attaches that to the pointer. And then those pointers just flow out into the system. And when you use the pointer, it takes the address, hashes it, encrypts it with the key, and then checks to see, is the PAC that's associated with this key the PAC that I just produced with my knowledge of the internal key. The key is internal to the hardware. It's not even unlike PointGuard, the key is not even anywhere in memory. It's in an internal register. It's generated when the system boots. So it's a very powerful way to, to prevent people from forging pointers. If I bring a pointer from the outside world, I need to guess what that PAC value is. Now it's only 16 bits. So, I have a 1 in 32,000-ish chance of guessing that right PAC value. But, in the process of attempting to do that, I'm going to probably dump a lot of core, get a lot of security violations when those PACs fail authentication, and someone's quickly going to find out I'm stopping this. And these were recently rolled out even in the iPhone platform, and it became available in ARM in their version 8.3 architectures and later. So really interesting technology. I think a very good one. Again, I'm a huge fan of any technology that can, make it hard to forge pointers, because so many attacks require the forging of pointers. So a big plus for this one. Now, interestingly, this attack was broke. This technology, after it was rolled out commercially, was broken just within, I think, weeks of that initial rollout. And, I invite you to go take a look at this attack. But Menja Yan, who's a professor at MIT, she did this really, really clever attack called Pac-Man, which the way it works is, if you remember Spectre and Meltdown from our from 2 lectures ago, the SideChannel lecture, it's basically a way where you run speculatively, and if you get faults or exceptions, all that code gets thrown away. And so how the way the Pac-Man attack works is you basically you inject from the outside world pointers that have guessed authentication codes, but you don't dereference those pointers on the correct speculation path. You dereference them on the misspeculation path. And so what happens is, if the PAC fails, the load that you try to speculate on doesn't occur. So there's no load. And so what you can do is you can load your data into the cache. You can speculatively check to see if the pack is correct, and it gets thrown away because it's on a misspeculation path. And so you can see if the number you guessed for the pack was correct, you'll see that the load occurred and displaced your data. And if the value for the pack was incorrect, you'll see the load did not occur because it was a security violation on misspeculation, but it just gets thrown away. No one knows about it. Silent. What a clever attack. I'm not even sure they can stop this. I'm really interested to see how this gets stopped. Right now, the stance is kind of like, oh, this is really hard to do, but I don't know. You know how security attacks always get easier and better all the time. This is a incredibly clever use of speculation to basically march through that 16-bit entropy space for the packs and very quickly find a valid pointer that you can use. All right. And and by the way, once you find a valid pointer, then you can very quickly reverse engineer what the key was. All right. Now let's take a look at another technology called Cherry. This is a really interesting approach to stopping memory access errors for languages that typically have a high susceptibility to memory access errors. We talked in the previous lecture about the use of safe languages and how safe languages can really help stop a lot of the issues associated with memory access errors, going off the end of an array or accessing storage after that storage has been freed. Well, if you don't have access to a safe language, which is very typical, like in an embedded framework, then you got to live with those memory access errors and the vulnerabilities that are associated with them. So what Cherry does is it adds what are called fat pointers to the architecture. And fat pointers are pointers that are bigger than 64 bits. They include other things like where you're pointing to. This is the original pointer. What is the length of the allocation, and what is base address? So it actually describes the entire array structure you're pointing into and the pointer into it, and then also permissions. Is it still allocated? Do I have read-write access to it, et cetera? And then it takes a 64-bit pointer and it bloats it into 256 bits. And they also have a 128-bit version. It's a little more lean than this. And so then if you go outside of the bounds of that array, and they even have techniques to find out when you've deallocated something with these permissions and such, then you get an exception. So it's really a cool way to find those vulnerabilities. This is really a detection and prevention technique for memory access errors. Some of the challenges here is it kind of breaks legacy codes because you've got to describe the bounds of your storage, which you normally don't have to do in C and C++. If you're writing some crazy program, you may not know the bounds of something. Also, there's interesting things people do, like XORing pointers together and indexing into the negative indices, as a way to, normalize access. It's just lots of crazy stuff that happens in C and C++, and that can break some codes. So that's an issue for this. But if you're writing new code, probably pretty easy to adopt this technology. And then Microsoft did a study a few years ago about how many of their vulnerabilities that they're fixing in their products were really based on memory access errors, and it was about 1/3 of their vulnerabilities. So privilege escalation and SideChannel attacks and other things that are not related to memory access errors directly may not be affected by solving this one problem. But this, everyone, I think, in the security community would agree that if you can stop memory access errors, that's a really good thing for security. So this is a really exciting technology, and doubly exciting because ARM, the company we talked about on the previous slide, is creating a processor called Morello, which integrates this technology right into the microarchitecture. So very exciting upcoming opportunity to see that architecture running with these technologies. In the SideChannel Attacks lecture, we talked a lot about inferring what's happening in the cache between two processes with the prime plus probe attack and a variety of other attacks. This is a wide range of attacks. So I want to want to understand what's this other process doing. I'm going to displace my data in my cache, and then I'm going to see if the victim process, when I ask it to do something for me, is displacing my data. The way it displaces my data, or whether or not it displaces my data, can tell me something about how that other process is running. And so we also saw in the last lecture ASLR, which is a way to randomize where stuff is in the address space. But still, in that case, relative address attacks, if I can learn one address, I can still figure out where the location of other stuff is. So that's a bit of a weak approach to not knowing where stuff is in the other process. Because if I can learn one piece of information, I can pretty much lock down everything else. So with randomized caches, what's going to happen is I'm going to decorrelate the location of data in the cache from the virtual address assigned to that storage. And by doing that, it is based on a key that goes into the cache, whether or not two pieces of storage in the virtual address space conflict. Now, when I try to build what's called an eviction set, what's an eviction set? That's where I'm displacing everything in one set of the cache. So a set, if there's a four-way cache, that's these 4 blocks. When I'm evicting everything in that one set of the cache, and then asking the other victim process to do something and to see if my eviction set got affected, the challenge with a randomized cache is, I can't build an eviction set because that's a cryptographically hard function. This is scatter cache, which what it does is it puts between the index and the tag an encryptor, so that the set index that goes into the cache is actually a cryptographic secret. And it's, as advertised, it's very hard to build a specific eviction set. So these are really interesting technologies. I think the challenge here in terms of security is, when I encrypt a piece of data that's 128 bits with a 128-bit key, figuring out what that final value is it's hard, right? Because there's the mapping between the plain text and the ciphertext is this full bijection of 102 to the 128 different symbols, and that's hard to figure out what that mapping is. But here I'm mapping, in a typical L1 cache, I'm mapping an 8-bit value to an 8-bit value, right? There's 256 lines in your cache. There's not a trillion lines in your cache, right? There's just, caches are physical things. And so the entropy in the set index is fairly small. And so you've seen reverse engineering based on that observation where, to kind of give you a sense, what they do is they take advantage of what's called the birthday conundrum. Like, oh, it's really hard to build a set in a specific location. But if I only have to build a set somewhere, that's fairly easy. And so, it's a little more difficult to implement attacks over that, but you can still do them in things like the scatter cache. There's also a notion of stochastic attacks. And I had a paper on this with one of my students, Teru Verma, in 2022. So you can go look at that paper, go to my Google Scholar and hunt that paper down. So we did what's called stochastic prime and probe, where basically we did stochastic prime. We just puked random addresses into the cache, and then it's like a coupon collector's problem where there's a certain probability for n of these lines that we touch that will create a fully primed set. And we know what that probability is. And then we ask the other process to do something for us. And there's a certain probability that it'll displace one of those things in that set. And so the product of those two probabilities essentially is like the channel noise. And then we use coding techniques and differential signaling techniques to really sort of deal with the noise of that scatter cache or various other randomizing cache channels. And we communicated through scatter cache, Caesar, many other new cache, many other kinds of randomizing caches. So given the limited entropy here, I don't see these as particularly durable defenses, but definitely throw a big wrench in your ability to figure out where stuff is. In the software-based attacks, third lecture, we talked about Rowhammer, which is this attack where we repeatedly hit memory in the same location And when you do that, you can flip bits in the adjacent lines to that aggressor row. And it has to do with charge coupling between the word lines of those DRAM rows, which are very tightly packed. And in this particular work, this is my work as well. We have this technology called Anvil. And basically all Anvil does is it just looks at the L2 cache misses, which it can sample using the performance counters on an Intel x86 architecture. And it just samples those on occasion to see if there's a high level of repeatability. It wants to see what's the entropy in that L1 miss stream. And if the entropy in the L1 miss stream drops below a certain level, we start refreshing those lines. This is because if you're doing a row hammer attack, the misses out of the L1 cache, the last level cache, the L2 or L3 cache that go to DRAM, there's not going to be much entropy there. They're going to be repeatedly hitting the same row. So what's nice about this protection for row hammer is it's not in the DRAM. It's just in the processor, and it's just trying to identify processes that are having too much locality to the DRAM, and then does selective refresh, which is just a load of a value in the line that you want to selectively refresh. And no hardware at all. It's just uses existing performance counters to do this. Really, really cool optimization. I think the challenge, though, is that the number of activations, which when we did this work was about 200 to 400,000 activations, that's been dropping precipitously as people get more clever about how to do activations. And also as DRAMs get, increasingly dense, as they always do. Today, it's about 5,000 activations to get a row hammer. So, that just may get underneath the entropy detectors of a technology like this. So again, I'm still scratching my head trying to figure out how to stop row hammer. Great research area if you're a PhD student watching this and you're looking for, way in an industry problem to work on. I see this as a really great problem. All right. Now I want to present a little bit more of my work. This is a project that I did with DARPA, which is the Department of Defense Research Agency. And this is my students, Mark Gallagher, Lauren Bernanke, and Alex Kissel, who Alex is now with me at Agita Labs, which I'll show you some of that work. It was just follow-on work that we commercialized out of Morpheus. And Morpheus is like the point guard work that I presented in the previous lecture, which is it encrypts pointers. The way it does that, though, is it encrypts pointers with, it's two advances over that work. It's all in hardware. There's no key in software to steal. And so it's like ARM pack in that regard. And then it uses a strong cipher. It uses a cipher called Simon. It doesn't use the full rounds of Simon, but it uses a lot of rounds. So it's actually significantly harder to crack than very, very weak XOR encryption. And then this does this thing called churn, which really tries to stop side channeling of those values by changing the underlying pointer values, how they're encrypted, by rekeying that every once in a while. So the students, when this paper got into ASPLOS, made a really cool video about this. So I'm going to play that right now.
In a world where software vulnerabilities are rampant and unsafe languages like C are exceedingly common, attackers are gaining more power by the second. To synthesize an exploit, attackers need access to an asset, such as pointer values. Defenses randomize these values to make it harder for attackers. However, hackers have found help around these measures. But there's hope. Because there's Morpheus. To stop attackers from de-randomizing assets, Morpheus changes it from under them in a process called churn. Morpheus is a secure architecture targeted at stopping advanced control flow attacks, such as ROP. We leverage hardware in RISC-V to provide two layers of defenses, displacing memory into a superimposed address space, and encrypting code and pointers. These defenses, combined with churn, significantly hinder exploits, With hardware support, Morpheus can churn sensitive assets every 50 milliseconds with less than 1% slowdowns. With information changing so quickly, attackers are left with a system that is extremely difficult to penetrate and must resort to advanced probing. Because of churn, this challenge becomes a race against a short clock, a race that is nearly impossible to win.
Awesome. Okay, so that was fun. It's always great to see your students do something you could never do, which is that. That's so much fun.
Find out more about.
All right. Let me go on to the next slide here. Okay, so Morpheus was a simulated design. Then Morpheus II, which Austin Harris and Teru Verma worked on, was a deployment of this technology into the cloud on F1 FPGAs in Amazon cloud. And so this was a full implementation. It was designed to run operating systems and applications with the Morpheus pointer protections engaged. And then it was red teamed by a commercial red team. Really interesting aspect to our DARPA program. All right, so just to describe how Morpheus 2 works, as you know, stated in the previous video, it encrypts code and pointers. So all the code everywhere is encrypted, and it's not decrypted until it hits the second stage of the pipeline. And that encryption is with a symmetric key based on a encryption cipher called Simon. And that key is just selected when the system powers on. So nobody knows that key. It's not accessible by software. And then there's a protocol when you bring software into the system to re-encrypt it under that key. So what's interesting about this, unlike, you know, Intel SGX and AMD SEV, where they decrypt things when they go into the caches for fear of you know, those high decryption latencies, we just kept it encrypted everywhere, so that it was always protected until it hit the pipeline. And then we basically ran Simon as many rounds as we could in a single cycle in this pipeline. Then you go through decode, and then you execute the instruction. So the only place the instruction is visible is in this part of the pipeline, nowhere else. And then we also encrypted code pointers as well, because the goal of this machine was to stop code injection. So code pointers are return addresses, as well as indirect function pointers, virtual table entries for C++, etc. It's any kind of pointer used to get to a piece of code. You jump through it. And so indirect jumps would get encrypted pointers. And so there was a stage between an indirect jump engaging and the fetch restarting, where we actually decrypted those indirect jumps. So everywhere in the registers, everywhere in the data cache, everywhere in a swap, etc., those pointers were encrypted. So that was pretty exciting. And you can see that those two defenses, just encrypted code and encrypted code pointers, we didn't even deal with data pointers in this particular machine, because we're just trying to stop code injection. That was our primary threat in the red teaming that we were addressing. By having them always encrypted, you really get a lot of resistance to a lot of different code injection techniques. Like you make buffer overflows really hard, because what is the pointer that I'm going to overwrite the return address with? This pointer is encrypted. I don't know the key, so I got to leak out a pointer. But if I leak out the wrong pointer, I don't know how to do relative addressing with a strongly encrypted value. I mean, there's no correlation between those values. So really a fantastic level of durability for stopping any kind of pointer forgery with this system. And I always like working with DARPA, because when you work with DARPA, you got to build stuff, you got to validate stuff, you got to put it to the test. And so in the DARPA program I was in, which is called the Sith program, there was a final effort called the FET challenge, where all of these designs, which were deployed on FPGAs in the cloud. Here you can see our local test board. That's a Xilinx UltraScale Plus FPGA. They were deploying our technologies into the cloud and then just making them available to attackers on the open web to attack. And then they would attack these targets for bounties. If they could penetrate these targets, they would get bounties. And so for us, it was remote code injection was what people are trying to do. And then one of the things, the goal of the Sith program was to actually stop basically protects systems against known software vulnerabilities with hardware defenses. So we actually had to have known RCE exposure in our, and this was in our SQLite code base. There were known code injection problems in the version that we deployed. So the attackers knew you can do code injection on these points in the program if the defenses are not engaged. But the defenses are engaged. Do the defenses stop this? And Morpheus was never penetrated. It was, in fact, the only target in the challenge. There were 7 total targets in the challenge. This is the only one that was never penetrated a single time. And really exciting result that really shows you when you make it hard for attackers to forge pointers, they're going to really have a really difficult time doing code injection. So that was exciting. By the way, our test application was a medical database, a medical registry. It was a database that brought together lots of mock medical data, and then you can make differentially private queries over that database. So they were hacking into this REST API into an SQLite database. So that was really exciting. And it was this idea that crypto would be a very powerful defense that got me more and more interested in using cryptography as a key defense in hardware security. And that quickly led me to the privacy community, because in the privacy community, I would say most of the defenses are really based on advanced forms of cryptography. Because cryptography, like I said in lecture 2, it's really the only superpower in the world of security. It's, you'll see 0-day software hacks until the end of time on big operating systems and big applications, but you don't often see people hacking into crypto systems and cryptography. That's very rare and usually a very big event. The example I always like to give is, when Alan Turing broke the Enigma cipher, they made a whole movie out of it. It's a really, really rare that you see strong ciphers get broken. Sometimes they'll get broken on the underlying implementation because it's got side channels, but a strong cipher with a clean, side channel free implementation is incredibly hard to penetrate. So we also talked about in the first lecture the difference between privacy and security. Security is stopping the CIA, the confidentiality, the integrity, and the availability hacking. PETS is about giving control of data back to data owners. And of course, you need good security to have good privacy. And so you really get the best security with crypto. So a lot of PETs, or privacy enhancing technologies, as they're called, are leaning heavily into cryptography. With a cryptographic strength defense, the system doesn't go down when the programmers go rogue, or the IT staff gets nosy, or an attacker arrives at your system and finds a vulnerability. That system goes down when someone guesses a very large key, and then that's very, very difficult to do. Very unlikely that'll ever happen. So examples of PET technologies, are for example, like differential privacy, which is a way of releasing statistics that don't reveal any individual in those statistics. Federated learning, which is a way to do machine learning training over many different data sets in different organizations. Instead of moving the data sets to a central location, you move the model to the various locations, and then you train the model across those different organizations. Data anonymization, where you're releasing data, but you're removing all the information that reveals the underlying producers of that data. And then secure computation, which is what I'm involved with, and I want to talk about some of my research in that, which is computing devices that compute directly on encrypted data. And they do this to preserve confidentiality of the data. And then some technologies, in particular the technologies I'm involved with, also perform what's called tamper-proof computation, where you're really limited to what computation you can run on a particular piece of data. And that's defined by the data owners, what computation you can run on their data. So let's take a look at this secure computation capability a little bit more. I'm gonna end up this tutorial specifically looking at this technology. By encrypting data and never decrypting it, and then having software operate directly on encrypted data, you're basically building a crypto wall between software, which is easy to hack, and data, which we want to protect. So what's interesting about this is if somebody hacks into that data, if somebody hacks into that system, they only get to see ciphertext. Now, if you do this right, you can really build sort of the Swiss Army knife of privacy enhancing technology, because what you're building is programming systems that operate directly on encrypted data. In a traditional system, if we want to send data to the cloud and have it processed, we have to send that data to the cloud encrypted with a key, or we have to send it decrypted to the cloud. The cloud will process that data and then send us back the results. With secure computation, oh, and then by the way, of course, as we've learned throughout this lecture series, if the data or the keys are available, attackers will get them. Malicious IT staff can get them. Programmers can do things that you weren't aware of with your data, et cetera. So with encrypted computation, we're going to encrypt the data before we send it to the cloud. The cloud will operate on the data, and software doesn't have access to a key. The hardware might, but software doesn't have access to that key. And so it has to compute directly on the encrypted data. And as a result, if someone hacks into that system, all they get to see is encrypted data. In essence, you're ignoring the vulnerabilities of the system, the vulnerabilities in the software, the vulnerabilities in the side channels, and you're applying the defenses not to the code, not to the system. You're applying it to the data that you care about by encrypting that data. By having the data remain encrypted, you're basically creating a very powerful isolation between everything that's happening in the software world and what's actually happening on the data. Now, you need the ability to compute on encrypted data, which is the big challenge of building these. Now, what they talk about in the pet world is this idea of zero trust data sharing. This is where I can take my genome, and I always like to use genome as an example of why privacy is important, right? If you give your genome to someone else and then they steal it or take it without your knowledge, or maybe you even agreed that they could take it when you signed the EULA to use their service, you've lost your genome forever. Now the world, that's part of their intellectual property. And you can't, unlike your password, you can't change your genome. Your genome is a one-time thing. So if I want to give my genome to a third party to analyze it, maybe show me my disease profile. Well, in a zero trust data sharing environment, I give them my encrypted genome. They analyze my genome encrypted, and they send me back encrypted results, which then I can decrypt. And then I don't have to worry about if they can see my genome or not. My trust is not in the company that I'm interacting with. My trust is in the privacy enhancing technology. And to me, that's really exciting, because that can really ease the tension between privacy and what people want to do with my data, like drive advertising or give me a service on my data, et cetera. It's really, really exciting. Now, one technology which you may have heard of is very, very popular in the press today is a technology called homomorphic encryption, and it provides this encrypted computation capability where I can send encrypted data up to the cloud. I can apply a function F to it, and I get the encrypted F of X back under that same key. And again, it eliminates all trust in both hardware and software completely. The trust is completely in the mathematics of the cryptography. And essentially what happens in these homomorphic encryption systems, in a traditional encryption system, you get an encrypt operation and you get a decrypt operation that takes a key, right? Okay. And so you encrypt values, you send them to your friend, they decrypt them. If you shared a key, okay, now we can see these values. In a homomorphic encryption system, there's two other functions. There's an add function and a multiply function. And the add function will take two pieces of ciphertext. You run this recipe on how to add, and you get the result of the two values added together in ciphertext, but never were the values decrypted. Now that's exciting. If there's a hack in the system, all they get to steal is ciphertext. There's not even keys there. If there's a backdoor Trojan in the hardware, no one's going to see anything except ciphertext. So it's a really exciting way to basically ignore vulnerabilities in the presence of HE computation. Super exciting. And it truly is a privacy technology, because now I can do I can get a computational service on my data and no one gets to see that data or the results of that computation except me. That's very exciting. In the cryptography community, they call it the holy grail of cryptography because it's the ability to compute directly on encryption. But if you follow the HE community in particular, you'll note that the performance is really, really poor. Compared to native execution, you're looking at thousands to millions of times slowdown, just legendary large slowdowns, and very hard to program. There's two kinds of HE. There's homomorphic encryption and there's fully homomorphic encryption, which is even slower than homomorphic encryption. And the difference between those two is how much depth in your computation can you incur. And normally you can only go about 4 or 5 multiplies deep in your computation, and then you destroy the data. Why? Because in an effort to not correlate the data to the values, they inject noise into the ciphertext. And so that noise accrues as you do deeper and deeper computation. FHE has this technology called bootstrapping, which can eliminate that noise it can reduce it to a lower level. And they basically allow you to do any depth computation, but it is incredibly expensive. So it's hard to program because now you tell your programmers, hey, you can write any program as you want as long as it's only got plus and multiplies, no less than or equal to, no equal to, no sorting, for example. Oh, and by the way, your depth of your computation will only be 4 or 5 deep. Ooh, that's challenging. So you see a lot of research building compilers to try and help make this a little bit better to do. And then also there's no such thing as integrity checking. If I send you my genome to do disease analysis in homomorphic encrypted systems, I can hack into that homomorphic encrypted system. I can throw away your genome and just generate a set of results that you have every disease and send it back to you. And you don't know that you may have every disease or you may have been hacked. You don't know that. That's because with integrity attacks, I don't have to see the data. I just have to manipulate the computation. And there is in HE, there's really no way to prevent the manipulation of the computation today. Now, there's an associated technology that can help in this regard called zero knowledge proofs, which you can say, you can ask it, did you actually compute this correctly? And to a certain extent, it can make some proofs about what was done and not done. Also very expensive. So anyway, you're just sort of layering expense on expense and expense here. So it's as traditional architects and compiler people, we're always shaving a few percent off. When you go into the world of homomorphic encryption, all of a sudden you're dealing with millions of times slowdown. It's a really different world out there. But what a cool technology. In my mind, this is really one of the greatest technologies in the last 20 years. The idea of computing directly on encrypted data is really sort of a ground shift in what you can do in the world of privacy. So exciting. Which is why I, as a hardware researcher, want to basically recreate all these technologies in the microarchitecture without actually doing all the advanced cryptography. And so what I've been doing for the last 5 years is basically doing what homomorphic encryption and zero knowledge proofs, and then there's another technology I didn't talk about called functional encryption, trying to recreate all of these very cool secure computation capabilities, but do it in the context of more advanced trusted execution environments, TEE enclaves. And that's really the focus of my work. So I'm just going to close this out by giving you just a taste of that work. So what I've been building are what I call cryptographically secure TEEs. These are TEEs where to penetrate them, you don't hack or do side channels. You have to guess keys. And so these are unique TEEs, quite different than traditional TEEs, but they're still TEEs. And they solve the 2 basic problems that we saw in the very first lecture of this series. They solve the problem of how do you stop software vulnerabilities, right? And you'll remember in the first series, I said software vulnerabilities are everywhere and they're hard to find and they're hard to stop. But if we want to have a cryptographically secure computation system, we have to find and fix all the trusted software vulnerabilities. That's a conundrum, right? If we can't find and fix all the software vulnerabilities, And in order to have a cryptographically secure system, we have to find and fix all the software vulnerabilities. The only solution is there can be no software in the trust zone. And this underlies my entire view of security in today's world, where a lot of people say that insecurity comes from bugs in software. But the way I look at it is insecurity comes from software, not bugs in software, software. So I just built a trust zone that has no software in it. So how does it become useful? Well, the interface to my trust zone is instructions. Add these two values together. It's basically a CPU. So there's no hard software in a CPU. So I can build basically a very flexible computation component by just building a CPU-like thing for my enclave. Then the other problem you have to solve is how do you get rid of side channels? And so we learned that there's, control, memory, timing, microarchitecture, analog side channels. And so what I do today in my research is I give the enclave its own silicon. And I build the silicon in a way where it provably has no control, memory, timing, and microarchitecture side channels. This is mid-2023. In a few months, I have a paper coming out in ACM CCS, really great security conference on those proofs. And so we've completed those proofs, and there are no side channels in the enclave that I built. It still has analog side channels. So the way we prevent people getting access to those analog side channels is we just put it into dedicated hardware in the cloud, and then we don't allow people to, wheel in their electron microscopes into the Microsoft Azure, Amazon AWS. So that's a pretty good solution as it stands today. But in particular, in my own research, I'm very interested in getting rid of analog side channels. Not really getting rid of them, but creating systems where you don't learn anything by looking at their analog characteristics. And then what you do is outside the enclave, just encrypt everything, right? So a strong, semantically secure encryption is a superpower. Use it everywhere you can. And so anywhere outside the enclave, if it's protected data, it's encrypted all the time, everywhere, in the registers, in the caches, in the memory, in the swap, everywhere. And so that's really, to my mind, is the way you make a cryptographically secure TE. So we have this technology called sequestered encryption, and we built this enclave, and I want to show you how that works. So sequestered encryption, the name comes from the fact that what we're going to do is we're going to sequester into this hardware enclave all of the computation on encrypted data. And inside that enclave, which is coupled with a core, that enclave inside of it is just a functional unit. There's no memory, registers, nothing. It's just a functional unit serving a tiny little instruction set extension to the main core. And the trust boundary of the enclave is just the functional unit. So what is trusted in the system is this functional unit, which is the only thing in the system allowed to compute on this encrypted data. It gets this data from a third party using what's called public key exchange. The functional unit actually has a public-private key, and a third party can encrypt that data and bring it into the system and unseal it inside the functional unit. The functional unit has a PKI decryptor, but no timing side channels. We saw that in lecture number 4. We built that with no timing side channels, provably. And it can expose a key inside this little hardware device. And then the hardware device just decrypts on entry, does computation on the data just like it would do it in the main core, and then re-encrypts it with a high entropy cipher. It's a high entropy cipher because it's going to inject a lot of random salt, as it's called, into the encryption. And what's coming out of the output of this functional unit is just pure random data. It's literally a fantastic random number generator. And so that now you have ability to do computation. You've taken this CPU, which is eminently hackable, and now you have this stream that you can send through the stream of computation. You can send through this SE enclave, which is both encrypted and not visible to any hacking or IT staff or anybody or any software, and then also has integrity checking in it as well. So really exciting technology. And just give you a sense of what you get from this enclave, you get this high entropy encryption mechanism where the entropy is so high, it's about 64 bits of entropy on any encryption. it's so high that essentially you're never going to see a piece of ciphertext that comes out of it again, ever. I mean, you'd have to run the thing forever and ever and ever just to have even a probability of seeing that ciphertext ever again. And there's no correlation between the data that it's working on encrypting and the output of the ciphertext. It's just pure random. And then it just gives you a risk-like instruction set to compute on data in a way where that data is integrity checked and that data is encrypted. So if somebody hacks into the system, we don't care about vulnerabilities in software at all. There's no software that can see access to the decrypted data. And in terms of hardware vulnerabilities, we only care about hardware vulnerabilities in the enclave. That's the root of trust for this computation stream. Anywhere else in the system, if someone row hammers your data, it's going to be encrypted. If somebody does a Spectre and meltdown on the main core, they're going to pull out your encrypted values. So it's as I said earlier in the earlier lectures, you should have encrypted that. With this technology, you can encrypt that. So it's really handy to have that ciphertext everywhere else. And then what guardrailing is it's the integrity checking. And we have a really cool mechanism called data flow integrity checking, which essentially can allow us to see what program produced a value. And then we also use that to selectively release values. So if I'm doing machine learning training over encrypted data, I don't get to see the results of that machine learning training, but the data owner could allow me to look at a single error variable to see how much error did I have in my training test in the last epoch, and should I continue to train this data? So really interesting capability and just generic privacy enhanced programming. By the way, over in the crypto world, you got HE doing this data encryption and encrypted computation, and you got zero knowledge proofs kind of giving you the capability of guardrailing. It's a way to see if someone did hack into your system and change what it was computing. But you really don't have anything in terms of safe data grants. And this is a definite limitation of the crypto world. How do you produce a piece of information that can be seen without giving your attackers the ability to see that data? So we've deployed this enclave in Azure and AWS. The way we deploy it in the cloud is on FPGAs. And we deploy our SE enclave into the FPGAs, and then we program to it from the main core via a memory mapped IO interface. And so the enclave is pretty small. It only takes about 6% of an ultra-scale FPGA, which is about 190,000 gates of logic. And it itself is logic locked. We saw that earlier in this lecture. It's watermarked, which means that we can actually tell if it's our hardware. And then it has technology called forward secrecy, where if we rebuild the hardware, we can't see old data that was able to be opened with a previous version of the hardware. It took us about 2 years to build this. 2 people, 1 year to build this. And it competes very effectively with homomorphic encryption and multi-party computation. It competes also with TEEs, but its security profile compared to a TEE is much better. Less side channels, no exposure to hacking because there's no software in the trust zone. And here's some performance measurements. When you look at the performance of TrustForge Azure compared to native code, so it's like your best algorithm that you've done versus a privatized version of the algorithm, it runs the code about 55 times slower, and that's primarily due to the latency of pushing crypto through the PCI bus to the FPGA card, and then the processing, decrypting and encrypting of that. So, if you're using Intel SGX, certainly faster than this technology. The main advantage of this technology over Intel SGX is this is a privacy technology that limits exposure of data from third parties in the system, whereas SGX, to limit that exposure, you're going to have to address side channels and software hacking in a real durable manner to do that. Compared though to homomorphic encryption, it's significantly faster. Microsoft CLHE is probably the most performant homomorphic encryption platform, and also one of the hardest to program. And it's more than an order of magnitude faster than that. And then if you look at fully homomorphic encryption, it's just literally millions of times faster nearly millions of times faster than those platforms. And what's really exciting about a hardware technology like this is the tighter you integrate into the CPU, the faster it'll get. So, while we're 55 times slower than native today, if we get on integrated FPGAs, we're about 18 times slower. It's about 3x performance improvement for that. If we can get into an ASIC on an SoC, which we're definitely working in those directions, you can get within 5x of native computation. And then if you integrate this completely into a CPU as a first-class functional unit, we've shown with Gem 5 simulations that you get within 20% of native. And that's just a first cut at optimizing that interface and those operations in the functional unit. So really excited about this direction for privacy enhanced computation. Programming the system is really quite straightforward. The computation is bit for bit compatible with the main program. So you're basically just taking variables that were not encrypted and then redeclaring them. For example, in C++, one of the languages it supports, you just have a set of variables which are encrypted. And when you do computation on encrypted variables, the results are encrypted, so you can't decrypt anything. And that computation is directed to the enclave. There's two things you can't do on encrypted computation, which we learned about in the side channel lecture. You can't use it to influence an if statement because that would be a control side channel. So the way you make decisions in encrypted computation is use a encrypted CMOV operation. And then you also can't index memory with a secret value because that would create a memory side channel. So the way you get rid of that is just use what's called an ORAM, an oblivious RAM primitive. Pretty simple change. These do cause some performance implications in the underlying program, but we found in general, if you redesign the algorithm, you can generally get rid of most of these overheads, in particular ORAM primitives. I always tell my team, like, using an ORAM primitive is a warning sign. It's like drinking in the morning. If you're doing it, you've got a problem. So if you need to use an ORAM primitive, just redesign your algorithm so that you don't. And what's really exciting about privacy technologies, this, be it sequestered encryption or homomorphic encryption, it's really exciting to see how you can build systems that are more privacy oriented. So I just wanted to close out this lecture with two examples of this. The first one is a medical registry database. This is a very common construct in the medical community where hospitals pool their data together and then give access to researchers. Typically, the access will be through some differentially private interface. So you're not revealing information about the underlying patients. You're not violating any HIPAA laws. So you want to encrypt that data in the database, preferably under each hospital's key. You want to be able to do encrypted computation across the database to generate analytics about that data. You want to guardrail that for two purposes. You don't want anybody to hack in and change your analytics. And then also you may limit the analytics based on who's accessing the database or what study is being done. So you just can't go arbitrarily probing through the data. You're only allowed to run the particular computations that are allowed based on the data itself. And then finally, to see those final results, you could add tests like, is this result differentially private? And if it is, I can then release that result to the third party. So it's really exciting what you can do with these privacy enhanced systems to really protect patient data in this case. Here's an IoT application that's super exciting where you've got basically a watch that is monitoring your heart data. It's encrypting your heart data on the watch. Today, it sends it up to the cloud where it gets decrypted. That data is fully visible. And you can infer all kinds of things about what's happening in your life by looking at your heart data. Your heart follows your emotions one for one, pretty much. But anyway, let's say you didn't want the cloud providers to know what's going on with your life. So you want to encrypt that data, send it up to the cloud, use a privacy enhancing secure computation technology to compute directly on that data. Use guardrailing to make sure no one hacks in and says, "Oh, you have an arrhythmia," or without make sure you're getting valid computation. Make sure no one's analyzing your data in ways you didn't want to. And then, really none of that data should be visible to them at all. They should all come back to your watch and be decrypted and shown to you on your watch. But there are cases where it would be useful for the server to see something. Let's say there's an arrhythmia analysis algorithm, and all of a sudden they start noticing you're having arrhythmias. Well, the server could get a data grant to decrypt that one arrhythmia value and just see that one Boolean value. And if it saw that you were having arrhythmias, it could send you a text message or an email, something to notify you that, hey, something's going wrong. So really interesting IoT applications. There's interesting applications in, criminal law enforcement, as well as, fintech, all kinds of really cool things. And I'm really excited about the possibility of using privacy enhancing technologies like homomorphic encryption, like sequestered encryption in the future to really ease that tension between, privacy of data and then enabling discovery over that data and enabling, safe monetization of that data, safe sharing of that data. I think these are really exciting technologies to explore. That is the end of this hardware video tutorial, the hardware security video tutorial. If you've stayed with me this long, thank you very much. I really appreciate it. It's been a pleasure to do these 6 videos. I'll be looking for more opportunities to do more tutorials in the future and more videos. So definitely like this video if you like this series, and please subscribe to my YouTube channel, because I tend to make videos on a pretty regular basis. Thanks again for sticking with me. Thanks again for watching. If you have any questions, don't hesitate to reach out. I'd love to interact with my viewers, and take care.